Everyone. So today we are going to discuss this paper TableNet, and this paper is a deep learning model for end-to-end table detection and tabular data extraction from scanned document images. So first, here is some keywords: deep learning models, of course, and end-to-end table detection and tabular data extraction from scanned document images. So key findings from this paper is like this paper discussed about table detection. So some of the work already been a huge progress have been done in table detection, and if we talk about table structure recognition, so that also there is a nice progress over this table structure recognition. But when we it comes to table data extraction, so there is problem because of uh, table detection involves like a lot of uh, like more fine-grained table structure needs to extract data from the table. So it involves more fine-grained table structure, like fine-grained table structure means row or column recognition. So that's why still there is a big problem with the table data extraction. So this paper has proposed a approach for table data extraction and pre-trained so how they have done this task table data extraction, although they have merged these both table detection and table detection and this table structure recognition with table detection. So they have given all three concept into single paper. Before that, lot of study have been done individual on table detection. Some of the study have been done on table structure recognition, and now this paper have merged all the three techniques into a single paper and contributed toward a data set also. So they have created data set also. They are calling it marmot data set, and so they have used this pre-trained BGG19 model for image on ImageNet data set. So this pre-trained BGG19 model they have used, and then they fine tune it for their task. So they are calling this as transfer learning. Of course, we know we train a model on a large data set or some other data set, and we can change it for other domain or other task. So that is transfer learning. So that's why there is a concept of transfer learning they are discussing in this paper. And one more thing is like fully connected layer they are also discussing. So and their results they have find reproduce or find on this IGDAR dataset and Marmot dataset. So these are overall description what they have done, and now comes to how they have done all these things. So they are saying that information inside trap inside this document images like receipt, like insurance claim forms or financial invoices, so any type of tables, lot of information is trapped inside that in unstructured document, right? So that's why we need this table detection, extraction, and recognition, all these processes. So here that they are saying that this table detection, table data structure recognition, and this detection, recognition, and extraction, all three have done. And here they are saying that VGG19 features, written VGG19 features they are using. And then what they have done on this. So this is followed by two decoder branches. First decoder branch is segmentation of the table region, and second a decoder branch is segmentation of the column. So there is two things. Remember this: segmentation of the table region and segmentation of the column within a table region. So again, segmentation of the table region and segmentation of the column with the table region. Okay, so don't confuse between these: table region and column within the table region. So two things are they are segmenting here. And for this purpose, so they are taking some images, input images. So the model takes a single input image and produces two different semantically labeled output images for table and column. So here also they are saying that semantically labeled output images for tables and column, these two processes. Okay, and the model shares the encoding layer of VGG19 for both the table and column detector. So while the decoder of the two tasks are separate, yes, because both tasks are separate, so that's why a decoder are separate. Okay, and the shared common layers are repeatedly trained from the gradient received from both the table and column detector, while the decoder are trained independently. So semantic information about elementary data type is then utilized to further boost model performance. So the utilization of the PGC19 as a base network, which is pre-trained on the ImageNet dataset. So this is what I have discussed earlier, that they have used pre-trained network, base network as BGC19, and they pre-trained that on ImageNet dataset, and then they have used their low-level feature and by a training over ImageNet. Okay, so this is up to that. Okay, all right. So, performance of this table net is on IGDAR 2013 data set. So, what is this? IGDAR 2013 data set. All right. So here they are saying that summarizing their contribution. So first contribution is their table net structure. It means architecture of deep multi end-to-end deep multi-task architecture for both table detection and table structure recognition. So that is table net architecture. So no, it is performing a good state of the art results on IGDAR and Marmot dataset. Okay, and then they have demonstrated that adding additional spatial semantic feature to TableNet. So here some spatial semantic features to TableNet have been added during training. So this will further boost model performance. So this is one more thing. And so what was first thing? First thing is TableNet architecture for table recognition and detection. Okay, and then by learning a spatial semantic feature, boosting the model performance. Third, pre-trained TableNet model and fine-tuning on another new data set. So that will also boost the performance of the model into new data set. All right, and the last one is manually annotated the Marmot data set for table extraction. Okay, and we'll release the annotation for the community. So this is all about four contributions. So related work are saying that or some of the individual work are already done in the field of table detection, a lot of work already done in the field of recognition, but when it comes to data extraction, so this is still a hard problem. So there are a lot of contribution previous authors have given. So for this paper they have given a TableNet model. So TableNet model, what is it doing? Model for table and column detection, two things there. It is detecting table and column. Okay, not okay. So here, so they are saying that okay, I think we should read this once. So in the prior deep learning based approach, table detection and column detection are considered two separate or different problem. Okay, so which can be solved independently. However, intuitively, if all the columns present in a document are known a priori, right, this is what, so the table region can be determined easily, but by definitions columns are vertically aligned uh, to or numerical blocks, right? Columns are vertically aligned word or numerical blocks. Okay, so thus here this thing, so thus independently searching for column can produce a lot of false positive, and knowledge of the tabular region can greatly improve results for the column detection. So what they are trying to say here, that instead of detecting complete table, they are independently searching for columns, so that it will improve results by producing a lot of false positive, and knowledge for the tabular regions can greatly improve, right? So this why, because since the both tables and columns have common regions, therefore if convolutional filter utilized to detect tables uh, can be reinforced by column detecting filters, so this should significantly improve the performance of the model. So their proposed model exploit this intuition, and is based on the long et al. This paper 15. So encoder decoder model for semantic segmentation. They have used this model for semantic segmentation. As previously we have seen that semantic segmentation is also they are doing for column and table detection, so that performance will improve. Okay. So here, the encoder of the model is commonly common across both tasks, but the decoder emerges as two different branches for table and columns. So concretely, they enforce the encoding layers to use the ground truth of both table and columns of document for training. Okay. So, however, the decoding layers are separated for table and column branches. Decoding layers are separated for table and column branches. Remember this. So, that's why there are two computational graph to train. Two computational graph is for one for table, one for column branches. Okay. So, the process is like the input image for the model is first transformed into RGB image, and then it resized to 1024 into 1024 resolution, and then once converted to RGB image and resizing operation, this modified image is processed using TableNet OCR, because need to extract data from this table now. That's why they are using TableNet OCR. Okay. So since model produces both output mask for the table, this is also one term that they are producing output mask, and for table and for column region. Okay, for both, for table also, for column regions also, these two independent output have binary target pixel values, and depending on whether the pixel region belongs to the table and column regions or background respectively. So the problem of detecting table in document is similar to the problem of detecting objects in real world. Okay. So again, the problem of detecting table in document is similar to problem of detecting object in real world images. It's like same problem. Whether you are detecting object in the real world images, or you are detecting table in the documents. Okay. So similar to generic object detection problem, visual feature of the table can be used to detect tables and columns. So the difference is that the tolerance for noise in table column detection is much smaller than the object detection. What is difference? The difference is, again, the difference is that the tolerance for noise in table and column detection is much smaller than the object detection, because object detection have number of object, but table or column detection is like a limited thing. That's why I have less tolerance. It means should have a tolerance for noise in table and column detection. Therefore, instead of regressing for the boundaries of table and columns, they employed a method to predict table and column pixels, region pixel wise. So, recent work on semantic segmentation based on pixel wise prediction has been very successful. So, FCN architecture proposed by this paper has demonstrated, another paper, so has demonstrated the accuracy of encoder decoder network architecture for semantic segmentation. So it's like complete process they are saying is first, transforming image into RGB, then resizing into 1024 into 1024 resolution, then OCR they are using, then masking for column or table, and then after masking they are using the pixel regions. So pixel region they are using, I mean binary target pixels they are using, and then they are saying that the problem becomes same as object detection problem, so that they are so that semantic segmentation based on pixel wise prediction they are using here, and then for that FCN architecture has been demonstrated the accuracy for encoder decoder network for semantic segmentation, because they are using semantic segmentation here, that's why they are using FCN architecture. Okay, so here the FCN architecture uses the skip pooling technique to combine the low resolution feature map of the decoder network with the high resolution features of encoder network. So VGG16 is used as the base layer in their model, and fractionally strided convolution layer are used to upscale the found low resolution semantic map, which is then combined with high resolution encoding layers. So right, okay, so their model uses the same intuition for the encoder decoder network as FCN architecture. So they proposed model as shown in figure, this is their proposed model. Let's see what is happening here in their proposed model. So this is image converting into 1024 into 1024 after RGB conversion, and so it's like this is a sample image from Marmot data set. So the Marmot data set contains these kind of images, and then the TableNet architecture proposed model consists of pre-trained layer of VGG19. So these are all pre-trained layer of VGG19. So this is for column here in the last layer, or yes. So layers starting from this what from convolution 1 to convolution 5. Okay, so layers starting from convolution 1 to pool 5, this is convolution 1 to pool 5, okay, are used as common encoder layer for both table and column graph. So as general encoder works, so it is working as same. So two decoder branches, now these are decoder branches after this pool 5 layer, pooling layer. So this is finally a pooling layer. So after this pooling layer, two branches are there, one is for table and one is for column graph, one is for table graph, one is for column graph. So two decoder branches, convolution 7 column, convolution 7 rows emerging after encoder layers. Before that, all are encoder layers. Let me use some pen. Yes. So up to this convolution 5. Sorry, not good in drawing and good at drawing. Okay, so up to this is encoder. Okay, after this two subgraph, this is first subgraph, this is second subgraph, one is for table, one is for column. Okay, so that's what they are saying, that two decoder, this is encoder portion, these are decoder. Okay, right. So two decoder branches, convolution 7 column, convolution 7 table emerging after encoding layers generate separate table prediction and column prediction. So these are two different predictions, separate column prediction and table predictions. Okay, so after that Let's see this thing, because these are similar to that. Only just a brief discussion of this model. So their model uses the same intuition for the encoder decoder network as FCN architecture, and their proposed model, as shown in figure, we have seen that uses pre-trained BGC19 layer of the base network, the fully connected layer after pool 5 of BGC19, replaced with two 1-into-1 convolution network. So here, after pool 5 have layers have replaced with 1-into-1 convolution layer. Yes. So 1-into-1, two 1-into-1 convolution layers. So these are small. These two, if you can say, this is 1-into-1 convolution layer. CO and V. Okay. So these are two 1-into-1 convolution layer. This is base architecture, means VCC19 base architecture, and then layers are replacing here. And yes, so each of these convolution layer, means convolution 6, uses ReLU activation function followed by dropout layer having probability 0.6 plus dropout shown in figure. So following this layer, two different branches of the decoder network are appended. So this is according to the intuition that the column region is a subset of table region. So they are saying that column region is a subset of table region. This intuition they are using. So thus the single encoding network can filter out the active region with better accuracy with features of both table and column regions. The output of the convolution 6 plus dropout layers is distributed to both decoder branches. So output is here, you can say output is distributing to both the decoder branches. Okay. So in each of the branch, additional layers are appended to filter out the respective active region. So here you can see these are they are talking about these prediction here. Okay. So here in the table branch, decoder network and architecture 1-into-1 convolution layer, convolution 7 table is used. Okay, so before using a series of fractional strided convolution layer for upscaling the net image, the output of convolution 7 layer is also upscaled using fractionally strided convolution and is appended with the pool 4 pooling layer on the same dimension. All right. So similarly, the combined feature map is again upscaled and the pool 3 pooling is appended to it. Finally, the final feature map is upscaled to meet the original image dimension. In the other branch for detecting column, there is an additional convolution layer with a ReLU activation function and a dropout layer with the same activation probabilities. Okay, so this is process that you have to read, because you cannot skip any step, because this is a complete process architecture. So you have to know if what is actually happening here. So that's why I'm reading complete paragraph. Okay, so right, so where we were, okay, let's, so in yeah, so we have discussed about first branch. Okay, so in this other branch for detecting column, so if in the other branch of detecting column is here, this one first, this one we have discussed. So now come to, in the other branch of detecting column, there is an additional convolution layer, column layer 7, and convolution 7 column with a ReLU activation function and a dropout layer with the same probability, dropout probability. Same dropout probability means 0.8. Okay, 0.8. right? So here the feature map are upsampled using fractionally staggered convolutions after a one-to-one convolution layer. So the upsampled feature maps are combined with the pool 4 pooling layer, and the combined feature map is the subsampled and combined with the pool 3 pooling layers in the same dimension. So they are upsampling and combining with pooling layers. And here, okay, so here the intuition behind using one into one uh, after this layer the feature map is upscaled to the original image. So in the both branches, means first branch and second branch, multiple one into one collaboration layers are used before the transposed layers. So the intuition behind using one into one convolution is to reduce the dimension of feature maps, which is used in class prediction of pixels. Since the output layer, means output of encoder network, must have channels equal to the number of classes, that is channel with max probability. So this figure you can see, this is showing the raw document image. Means this is a raw document image, and then uh, generating a table mask after processing, and generating column mask after processing. So these are two kind of masking. All right. Yes. So now come to this row table row extraction. So here they are saying that they are using this OCR for extraction, and then three rules for row segmentation they are using here. So first rule is, in most table for which line demarcations are present, the line segment the row in each column. They detect to detect the possible line demarcation, means for rows, every space between two vertically placed words in a column is tested for the presence of lines by a radon transform. So the presence of horizontal line demarcation clearly segments out the row, right? So another rule is, in case a row span multiple lines, if it have row spans multiple lines, the rows of the table which have maximum non-blank entries is masked as the starting point for new rows. So for example, in a multiple column table, some of the columns can have entries. Some of the columns can have entries spanning just one line, like quantity. So which others can have multi-line entries. Thus, each new row begins when all the entities in each column are filled. In tables where all the columns are completely filled and there are no line demarcations, each line can be seen as a unique row. So dataset preparation is like I don't think I should discuss this Marmot dataset uh, they have created. So yeah, so dataset was manually annotated by labeling the bounding boxes around each of the column inside the tabular region. Okay, and the manually annotated modified dataset is publicly released with the name Marmot extended for table region recognition. And then providing semantic information and training data. So first in this paragraph it is how they are providing the semantic information, and after that training data preparation for TableNet. So data preparation is like after we processed with TableNet OCR to get all the word patches in the image document. Then the word are processed via regular expressions. So how words are processing? Via regular expressions to determine their data type. Okay. So the intuition is to color the word bounding boxes to impart both the semantic and spatial information to the network. So each data type is given a unique color and bounding boxes of word with similar data types are set in the same color. So word bounding boxes are filtered out for remove spurious detection. However, since word detection and extraction from the OCR will produce some noise. So yes, it can produce some noise because once you are detecting and extracting word from the OCR, it definitely there is some no, there can be some noise for model to need to be learned or is need to be resilient to these cases. So therefore, the simulation for this have been simulation for so therefore, to simulate the case of incomplete word detection in the training image, a few randomly selected word patches are dropped deliberately. The formed color coded image can be used for training, but many visual features like line demarcation, corners, color highlights, etc., are lost. So while using only the word annotated document image, therefore to retain those important visual features in the training data. So the word highlighted image is pixel wise added to the original image. So these modified documents images are then used for training. So experiment and result is performed for table detection and for table data extraction both. So here is like they have used uh, like how much iterations, like coding perspective, pre-trained model they are using. So what optimizer they are using? So Adam optimizer it's like 5,000 iterations and learning rate of this, and so that's why some hyperparameter settings for this experiment for both table recognition and table detection and for table data extraction. Okay. Okay, so after that there is conclusion. So conclusion is like this paper okay, so conclusion is this paper presents TableNet model, a novel deep learning model trained on dual task. For the dual task is table detection and structure recognition in an end-to-end fashion, and existing approaches to information extraction, treat detection and structure recognition as two distinct problems to be solved independently. And then TableNet is the first model to jointly address both joint tasks simultaneously by exploiting the inherent independence between the table detection table search. This is what we already have discussed, like merging two tasks that was previously that was independently, and there's two tasks merging with detection. So in the future, they intend to train TableNet with third branch to identify row. So this is future work. What they will do. Okay. So I think this is all about this papers. Okay. Thank you. Thank you so much. Bye bye.